Hey guys, so in the previous lecture we were discussing stream trapping. So there were three types of principle in which we can trap the steam. So first we discussed was thermostatic trap, in which the trapping happens due to change in temperature difference. And then second is density trap. In this, the trapping happens due to change in density difference of entering fluids. Then thermodynamic trap. So thermodynamic trap sense the velocity difference of entering fluid. So we have discussed thermostatic traps, in which there were three types, that is expansion, balanced pressure, and bimetallic strips. Then we have seen density traps, which were four types, that is lever mechanism, free floats, inverted and open buckets. Then we were discussing thermodynamic traps. So we'll start with today thermodynamic traps. So as we know the principle that it depends on velocity difference. So these are designed to discharge condensate, a relatively slow moving fluid, such as a condensate water. So water's velocity will be lower than the flash stream. So a relatively high velocity fluid, when condensate enters the trap body, so when condensate enters the trap body, so it moves slowly relative to the steam. So it will move slowly to the steam, and it will be freely discharged. So when flash or live steam moves across the underside of the disk, its velocity is much higher than water, and the high speed creates a pressure drop which closes the valve head. So there are basic two categories of thermodynamic traps that work on velocity principle, that is thermodynamic disk and thermodynamic piston. So thermodynamic disk traps contains a disk which reacts to difference in velocity of condensate. So there is a disk in which will react according to velocity difference. So under a disk velocity under a disk creates a drop in static pressure which closes the disk. So which will close the disk. Subsequently, control chamber steam above the disk condenses due to heat loss, enabling the valve to open. So with the help of disk, it will control. Then there is thermodynamic piston. So in this thermodynamic piston arrangement, piston traps operate similarly to disk models. So it will operate similarly to disk but contain a piston which is centrally located pilot hole which constantly bleeds some combination of air, condensate or steam to actuate the valve open. So here there will be a piston cylinder arrangement. So this will bleed the valve with condensate, air and steam. So these were thermodynamic traps which are used for removing the condensate. Now, the next topic which we are going to discuss is condensate recovery and flash steam recovery. So, how we can uh, recover this? So, the steam condenses after giving off its latent heat. So when a steam will condense, so once it is given as latent heat, then and then it will condense. Okay, so in the heating coil or the jacket of the process equipment, so a sizable portion, about 25% of the total heat in the steam, leaves the process equipment as hot water. So 25% of the total heat in the steam leaves the process equipment as a hot water. So 25% is left as a hot water. So here there is a graph in which on the x-axis there is pressure, there is in bar. Then on the y-axis there is specific enthalpy, H in kilojoule per kg Kelvin. So this figure compares the amount of energy in a kg of a steam and condense it at the same pressure. So this is the amount of energy, and this is the amount of energy for condensate, and this is amount of energy for steam. So the percentage of energy in condensate to the steam can vary from 18% to 30% at 14 bar. So at 14 bar it can vary at 18 to 30%. Clearly the liquid condensate is worth reclaiming. That is, it has very much energy, and that energy is need to be reclaimed because it is having 30% of the total energy. So if this water is returned to the boiler house, so if this water is returned to the boiler, so it will reduce the fuel requirements of the boiler. So the fuel requirements of the boiler can be reduced. So for every 6 degrees Celsius in the feed water temperature, there will be approximately 1% saving of fuel in the boiler. So every 6 degrees Celsius rise in feed water temperature, there will be approximately 1% saving of fuel in the boiler. So 1% is saved. Therefore, after trapping this condensate through various traps, the recovery of the energy of this condensate is very much necessary. So this chart shows that how much energy we can recover. Then next is flash steam recovery. So flash steam is produced when condensate at a high pressure is released to a lower pressure and can be used for low pressure heating. So the higher the steam pressure and lower the flash steam pressure, the greater the quantity of flash steam that can be generated. So in many cases, flash steam from high pressure equipments is made use of directly under low pressure equipments to reduce use of steam through pressure reducing valves. So the flash steam quantity can be calculated by the formula given, that is S1 minus S2 upon L2, where S1 and S2 are sensible heat of high pressure condensate and low pressure condensate. S1 minus S2, high pressure condensate and low pressure condensate respectively. L2 is the latent heat of flash steam. So this flash steam can be used on low pressure applications like direct injection and can replace an equal quantity of live stream that would be otherwise required. So where live stream is required, there it can be used. So demand for flash stream should exceed its supply so that there is no buildup of pressure in flash vessel and consequent loss of steam through the safety valve. So generally the simplest method of using flash steam is to flash from a machine equipment at a high pressure to a machine equipment at a low pressure, thereby augmenting steam supply to low pressure equipment. So from high pressure to low pressure directly we can inject. So this is how we can use the flash steam. Then next topic is opportunities for energy savings. So what are the main opportunities? It is our main goal of ECM, energy conservation and management, that where we can save the energy. So there are total 6 points where we can investigate to save the energy. First is monitor steam traps. So to monitor the steam traps, so whatever steam traps we have installed, so we need to monitor it. An isolating valve provided in the downstream of a trap and test valve shall be provided in the trap discharge. When steam valve is open, condensate discharge in flash steam are required to be observed. So we need to observe this steam trap. So condensate discharge. So inverted bucket and thermodynamic disc trap should have intermittent condensate discharge. So for thermodynamic disc traps, one in intermittent means in between there should be a discharge. Then next is that in float and thermostatic straps should have a continuous condensate discharge. In other traps, there should be continuous, that is float and thermostatic traps. So continuous discharge is required. And thermostatic traps can have either continuous or intermittent discharge depending upon load. On load we can decide there for thermostatic. So if in inverted bucket trap are used for extremely small load, so it will have a continuous condensate discharge. So if the load is very small, then continuous discharge is required. So depending on load, we can fix the discharge for the condensate for different traps. Then next is for flash stream. So for flash stream, the users generally get confused between flash steam and leaking steam. So flash steam and leaking steam. So if steam blows out continuously in blue stream, it is leaking stream. If a steam blows out intermittently in a whitish cloud, it is a flash stream. So we got the difference that in flash stream is not continuous, it is intermittently, while in leaking stream it is continuous because there is a leak. So if continuous steam blow and no flow indicate, so there is problem in the trap. So that we need to differentiate that if steam is coming out, then it is not a leakage and it is a flash stream. The next opportunity for saving is avoid steam leakage. So it is a visible indicator of waste and it can be avoided. So it has been estimated that a 3 hole diameter a 3 hole diameter on a pipe having a pressure of 7 kg per centimeter square. So a 3 diameter hole in a pipe having pressure of 7 kg per centimeter square would waste a 33 kiloliter of fuel oil per year. 33 kiloliter of fuel oil per year. So to avoid leaks, it may be worthwhile to consider replacement of flange joints which are rarely opened in old plants by weld joints. So in this way we can avoid the steam leakage. Then third is providing dry stream for process. So the best steam for industrial purpose heating is dry saturated steam. Wet steam reduces total heat in the steam. So also water forms a wet film on heat transfer and overload straps and condensate equipment. So superheated steam is not desirable for process heating because it gives up heat at a rate slower than condensation heat transfer of saturated steam. So by this means we can save some energy. Then utilizing steam at the lowest acceptable pressure for the process. So from if you have seen the steam table, that it is clear that the latent in the steam reduces as the steam pressure increases. So as we have seen the diagram, that as the pressure increases, so the latent heat is reducing. The amount of latent heat is reducing as the temperature increases and pressure increases. So it is only the latent heat of steam which takes part in the heating process when applied to an indirect heating system. Thus, it is important that its value is kept as high as possible. So, this can be achieved if we go for lower steam pressures. So if steam pressures are low, so we can achieve that. So as a guide, the steam should always be generated and distributed at highest possible pressure but utilized at a low pressure as possible since it has higher latent heat. So this is the requirement how we can use the steam. Then minimizing heat transfer barriers. So the metal wall may not be the only barrier in the heat transfer process. There is likely to be a film of air, condensate and scale on the steam side. On the product side, there may also be a baked on product or scale or a film. So regular cleaning of the surfaces on the steam side may also increase the rate of heat transfer by reducing the thickness of any layer of scale. However, this may not always be possible. Then last is proper venting, air venting. So when steam is first admitted to a pipe after a period of shutdown, the pipe is full of air. So further amounts of air and non-condensable gases will enter with the steam. So although the proportions of these gases are normally very small compared to the steam, so very less, when the steam condenses, these gases will accumulate in pipe. So there is already air. So if the steam condenses, so this will accumulate in the pipe and heat exchanger. So precautions should be taken to discharge them. So it should be discharged before starting the process. So the consequences of not removing the air is a lengthy warming up period and reduction in plant efficiency and process performance. So it can reduce the efficiency and plant performance. So air in a steam system will also affect the system temperature. To also affect the system temperature, air will exert its own pressure within the system. It will exert its own pressure within the system and will be added to the pressure of the steam to give a total pressure. Therefore, the actual steam pressure and temperature of the steam air mixture will lower than that suggested by a pressure gauge. So proper air venting is essential, which can save significant amount of energy. Then next 7, 8 and 9 point. For 7 point, there should be proper insulation of steam pipelines and hot process equipments to avoid the heat loss, so which we can save energy. And this condensate and flash steam recovery we have seen before. So these are the main opportunities for energy savings. So this was steam system, completion of the steam system whole topic. So from next lecture we will see furnaces. So how we can classify the furnaces and how we can save the energy from furnaces. So we will see furnaces from next lecture. So thank you very much.